Hello, my name is Alberto Marquez. Welcome to this video in which we're going to discuss acceptance sampling plans. We're going to talk about attributes and variables and simple plans, multiple plans, and how basically they are computed and the parameters that they have. In future videos we will discuss more in detail on performance measures and other alternatives that we have when we have to decide how to execute or incorporate sampling plans in our organization. The learning objectives for this module include explaining the fundamentals of sampling plans, including the difference between attributes and variable sampling plans, what is the function of the sample size, the acceptance and rejection numbers, and we're going to talk about the advantages and disadvantages of using them. Also, we are going to talk about the simple sample plans and how the operating characteristic curves work, how do we design the sampling plans, and some performance measures including the average outgoing quality, the average outgoing quality limit, and the average total inspected. Similarly, for other plans, we have the double and multiple sample plans for attributes. We are going also to discuss how the OC curves are computed in that case, and the average quality limit and the average sample number. We're also going to talk about the military standard 105E and the Dutch Roman sampling plans, and what are the procedures and the performance measures, and we're going to have a brief discussion on sampling plans for variables. The fundamental distinctions that we have with respect to sampling plans is that we use sampling plans by taking a sample of a manufactured lot, and we're just going to analyze the sample, not the whole lot, and we're going to make a decision whether to accept the whole lot or not, depending on the characteristics that we find in the sample. This makes it very efficient in terms of not having to inspect all the lot, but also has some drawbacks. So we could have sampling for attributes, that is, we're going to count how many of the products are non-conforming, and we also could have a sampling for variables in which, for instance, we could measure the concentration of a particular component in the mix, and we would use percentage value for that concentration. So depending on the nature of the problem, we could use either sampling plan for attributes or sampling plan for variables. Every sample plan requires at least a sample size in their design, in which we know beforehand how many units are we going to sample. Also, we need an accepting and rejection numbers, which are C and R. If the number of defects that we find in the sample is less than or equal to the acceptance number, then we accept the lot. And if it exceeds the rejection number, then we will have to reject the lot. Talking about the advantages and disadvantages of sampling plans, it is convenient from the cost perspective because we don't have to inspect the whole lot, and in some cases it's the only option, for instance when we have to do destructive testing. So another benefit is, in many cases, for some products, the more you manipulate the product, the higher the chance of damaging the product. So we want to manipulate as least as possible. Also, we save on the fact that we don't need as much personnel or equipment or time into the process of making sure that the quality of the product is right. Of course, this is a sample process. We cannot be sure, but at least to make the decision with certain level of risk. And in general, it is a good strategy to reduce the defects that we have in the process due to accepting raw material that is not up to standards. Some of the disadvantages that we have is that we are running two types of risk. We can reject lots that are in good shape. We have a chance of finding too many non-conforming products within the lot, making the assumption that the whole lot will be in that situation, and it was just a circumstance of the random variations. Or we can also not detect lots that are faulty, but just again by chance having the possibility of not detecting or not sampling enough errors as to stop the product and reject it. So we run that risk. The sampling plan requires some planning, documentation. So there is some elements of administration that if the sampling process is not being taken care of, we may lose the benefits. So we must design properly the sampling plan to fully take advantage of it. Here we have a diagram that represents for us the flow of decision making that we have when we have a simple plan. Essentially, we need three parameters: the sample size n, the number of acceptance, and the rejection number. Typically, the rejection number is the acceptance number plus 1, in such a way that we know with clarity if where are we standing depending on the number of defects that we have. So in this diagram we have the lots arrive or are produced, and then we obtain how many defects are in the sample, and if the number of defects are in the sample are larger than the acceptance number, then we have to reject the lot. If the number is less than or equal to the number of the acceptance number C, then we would accept the complete lot. Here we have a comparison of simple sampling plans versus double sampling plans. On the left side, we already discussed that in the previous slide. Now, if we concentrate on the right-hand side of this slide, we have that the lot arrives or produce, and then we take a first sample and we obtain the number of defects in the sample. If the number of defects in the sample is not larger than the acceptance number for the first sample, then we accept immediately the lot. We don't need to go to a second sample. If, on the other hand, the number of defects exceeds the acceptance number, we need to ask a second question. Does this number of defects exceed the second acceptance number? If so, then we would have to reject the lot right there. If, on the other hand, the number of defects in the first attempt is larger than the acceptance number for the first attempt, but is not as large or is not larger than the acceptance number for the second attempt, then we need to take a second sample. And we obtain the number of defects that we are obtaining in the second sample. We compute the total number of defects, the ones that we had in the first sample, and the ones that we had in the second sample. We put them together, and now we compare that quantity against the acceptance sampling number for the second attempt. And if that's our final decision for a double sampling plan, if the total of defects exceeds the acceptance number 2, then we reject the lot. But if it's not exceeding, it's less than or equal to that acceptance number, then we can, in the second attempt, accept the lot. So the computation of the probabilities of accepting the lot in this case are depending on the previous results and the possible results, and we're going to discuss how to compute this. If we focus on what is the decision-making process that we have to have in the development of sampling plans, essentially we have to negotiate the amount of error 1, or the probability alpha of error 1, and the error 2, or the probability beta of error 2. And these two errors are associated with, first, the acceptance of the lots that should have been rejected. That's the beta error, and of course that's a non-desirable situation to receive into the production line lots that will affect our process, and that's associated with the beta, or error 2. Error 1 is when we reject lots that we should have not rejected, given that they came with the accepted level of quality. Here we have a table in which we depict how this process could be made. Let's say that first you want to have a sampling process for which the alpha error, the probability of rejecting lots that should have not been rejected, is 5%, as long as the actual number of non-conforming is 1%. So if it's 1% the number of non-conforming, you would expect to reject only 5% of the lots. In other words, the probability of accepting the lot is 95%. So this is a situation for attributes, and the acceptance number could be any discrete number, 0, 1, 2, 3, and more. Here we are depicting the situation in which the acceptance numbers are 0 and 1 or 2 or 3. So we are making the decision which one of these options to take. And the rejection number, in order to make the decision in a simple sampling plan, would have to be just the acceptance number 0 plus 1, 1, or 1 plus 1, 2, etc. So the first thing we need to do is, if we have an acceptance number of 0 and we have a proportional non-conforming of 1%, what should be the sample size that allow me to have a probability of acceptance of 95%? We can use the binomial distribution. Here I'm depicting the binomial distribution with the words with the letters BD. In Excel, you would have to type in the complete function binom dist, and the parameters that you have are, first, the number of successes that you want. The second parameter is the number of trials. The next one is the probability of the successes happening in each one of the trials, and the last parameter is a 0 if it's not cumulative and 1 if it's cumulative. So by trial and error, you can find that the closest number of the number of samples when the acceptance number is 0, in order to get a 95% probability of acceptance, is 5. The number of trials that you would need in case that the acceptance number is 1, that is, the total number that you are willing to receive is 0 or 1 defects in the lot. The cumulative probability of the cumulative binomial probability achieves 95% when the sample size is 36. And I can continue trying. For c equals 2, the number of trials would be 82. For c equals 3, the number of trials I need would be 137. And this would be the number of how big the samples would have to be, right? Of course, there is a big difference from sampling 5 specimens than to sampling 137 in terms of time and cost. So here you can perceive the trade-off of what we are going to have. So based on that, we can decide, well, if we go with c equals 0, the sample size would have to be 5. is equal, if C is 1, the sample size would have to be 36. If C is 2, the sample size would be 82. And then as a reminder, the sample size, the acceptance number C is that number or anything below, so the probability that we're computing is the probability of having 0, 1, and 2 when C is equal to 2, and the most convenient sample size would be 82. Finally, when the sample acceptance number is 3, the sample size would be 137. But that has an impact because we also want to have a moderate beta error. And the negotiation that we could have is we want to know what is the beta error when the actual proportion of non-conforming is 12%. In other words, when the product that does not passes the specifications would not be 1%, but now has increased from 1% to 12%. We want to know what is our risk of not detecting that. So the last row on this table, we can see that the beta error when we selected an acceptance number of 0 and a sample size of 5, but the number of non-conforming change from 1% to 12%, the chances of accepting that lot would be 52.8. In other words, you have much more defects and you still are accepting over 50%, more than half the lots. If you proceed to get more information, the sample size, you increase it from 5 to 36, then the beta error reduces from the previous number to now only 5.9%. And that is convenient because if now you have more defective, you have 12% defective product in the lot, you have only 5.9% chances of not detecting that the lot is bad. If you proceed and extract even more information with a lot with a sample size of 82 at the same percentage of defective or non-conforming 12%, the chances of you not detecting that is only 0.2%. So here you see how this trade-off happens. You are still willing to reject 5% of the lots, but because you are extracting more information, the risk, the beta error, or the probability of accepting a lot that should have not been accepted is being reduced. Finally, in the last computation, if we use an acceptance number of 3, we can increase the sample size to 137. With 137, if we have a non-conforming of 12%, we have virtually 0% chances of not detecting when the number of defectives in the lot is 12%. And this is what we need to do, and we are going to discuss in the next video how in detail can we execute these operations.